So, hello to everyone who's watching on YouTube. So, since no one has joined the session in person yet, so I'll be waiting for like, let's say, 5 minutes so that a few people can join the session in person also. So, I guess we'll get started in 5, 6 minutes. Okay, since no one has joined the session in person yet, so I guess we can get started. And if someone comes along, I can take their doubts as well. So, just to reintroduce myself to the YouTube audience. So, hello everyone. I'm Lakshay Saggi, the TA for the problem solving sessions for the NPTEL Competitive Programming course. So this will be our eighth session, and in this session we'll be talking about problems related to max flows and yeah, stuff like that. So the problems will be based on this week's content only, like always. So I have a bunch of like eight problems for today. Sorry for that, guy. So I guess we can get started with discussing the problems then. So let me just share my screen, I guess. I'm just sharing my screen. Okay. So I hope my screen is visible to everyone since no one is in the meeting yet. So I won't be able to know if there are any issues. So I guess I'll assume that my screen, everyone is able to see my screen. So yeah. So, okay, so let's get started. So today's session we have a bunch of like eight problems to discuss. So it won't be that long of a session, but yeah, I believe it will still take us some time as the concept of max flows is new to us. So once again, like all sessions, I'll be assuming that you guys have went through this week's lectures, and so I'll be assuming that all of the things you already know, and we'll be just coming straight down to solve the questions. So yeah, so I guess we can get started with the first question. So first problem says that in the Ford-Fulkerson algorithm, what is the residual capacity of a forward edge? So I hope everyone remembers what Ford-Fulkerson algorithm is. It is used to find the max flow, the SG max flow in a graph. And now the problem is just asking in the Ford-Fulkerson algorithm, how do we define the residual capacity of a forward edge? So what it means is that now what do you mean by the residual capacity of the edge? So this is just a knowledge-based question or just a straightforward question. So the so it's not the maximum capacity, it's not the flow going through the edge, but is instead the maximum capacity of the edge minus the flow in the edge. So remember, guys, if you guys remember in the Ford-Fulkerson algorithm, what we do is if we pass a flow F from an edge of capacity C, then we say that the remaining capacity on that edge is of C minus F. And in the backward direction, we put an edge of capacity F. So we put a forward edge of capacity, maximum capacity minus the flow in the edge, which is equal to C minus F. And that's what we call the residual capacity of the forward edge. And for the residual capacity of the backward edge is then just the equal to the flow in the edge. So F is the residual capacity of backward edge and C minus F is the residual capacity of forward edge. So the C is the correct answer here. So yeah, let me just put this here also. That correct answer is option C. Just to put a note here that mhm, when we pass a flow of value F through an edge of capacity C, the residual capacity of the forward edge becomes C minus F. And as I said, we put the backward edge of capacity F. So the residual capacity of backward edge becomes. So these forward and backward directions are defined with respect to the direction of original edge. So if the original edge E was in some direction, then that direction will be the what we call the forward edge, and the direction opposite to that edge E will be what we call the backward edge. So yeah. So and the residual capacity of the backward edge becomes equal to F. Yeah. So something like this. So maybe I should put this node in bold, but yeah. So option C is the correct answer here, and I'll just underline this. So yeah. So after this, I guess we can move on to the next question then. So the second question is, so we are given this network. So we are given basically this graph between S and T. So and this is a directed graph as we can see, and every edge has some capacity. So the problem says that given consider the network given above with source S and sink T. So this is the source, this is the sink T, with the numbers denoting maximum capacity across a particular edge. So now we want to find out the value of the maximum flow in the given network. So the problem is quite straightforward. What the problem asks us is we are given the source and the sink, and we are just asked to find out the maximum flow in the given network. So what will be the maximum flow going from this source to this sink? So for this, we can just apply the algorithm which we have already discussed, which have been already discussed in the lecture videos. So we can apply any of Edmund Carr's algorithm or Ford Fulkerson algorithm. We can do anything. So maybe I'll just do this for everyone so that the algorithm actually, the implementation of the algorithm becomes a bit clearer, like what happens actually. So maybe we can try to apply for Fulkerson algorithm on this graph. So maybe I'll just draw this graph again for myself. So there are S, A, B, C, D, E, and T. So maybe I will draw this graph. So there's this node S. Okay, and so there are some other nodes given to us, which are A, B, C, D, E, and T. So the nodes are something like this. S, A. So yeah. So this is the sort of graph which we are given. Yeah. And the edge capacity is given to us are, so maybe we can rename these nodes. So this is A, B, C, A, B, C, D, E. So this is A, this is B, this is C. So I'm just drawing the graph again. So these are the nodes and this is the same D. So now we have edges from S to C, S to A, C to E, E to D. So yeah, something like this. These edges we have. So I'm just drawing this graph. And we also have to put down the capacities for these edges, which I'll do in a second. And we also have an edge from A to B. So yeah. And now this has capacity 12, this has 11. So maybe I should put down the capacities also. So 12, 11, 5, 5, 7, 5, 5, 5, 7, 5, 3, 4, 6, 9, 12, 3, 4, 6, 9, 12. So yeah, so these are the capacities. So this is the graph which has been given to us. And now we want to find out the value of SG max flow in this graph. Okay, so I guess we can apply Ford Fulkerson algorithm here now. So in the first step, what we do is we send some flow, we find a path from S to T and send some flow across it. So we can send the flow along any path. So let's consider this path. So let's say, so this is the initial graph. I'll make a copy of this graph also, and we'll be dealing with that copy. So let's say this was the graph, and now suppose I consider this path, the paths from S to C to E to T. So suppose we go from S to C, then C to E, then E to T. So this is the path I'm taking. So I'll say, so this path has a so the least capacity edge in this path is the edge with capacity 5. This edge E right now has capacity 5. This edge has capacity 12. This has 11. So I can pass a flow of capacity 5 through this path. So let's say I pass a flow of capacity 5 through this path. So what happens is this capacity of 11 becomes a capacity of 6. This 5 becomes a capacity 0. This 12 becomes a capacity 7. And we introduce some reverse edges. So edges in the backward direction will also come into picture now. And so this edge will now have a capacity. Okay, maybe I should. So I should put it at the capacity of 5. So this edge has a capacity 5. Similarly, another edge which comes into picture. Okay, I guess I'll have to insert another edge. So we'll insert here also a backward edge. And this edge will have a capacity 5. Similarly, I'll also insert an edge from C to S with a capacity 5. So let's just do it also. So yeah. So this is the residual capacities in this graph. Now, this has a residual capacity of 5, this has 7, this has 0, this has 5, this has 6, this has 5. And right now we have pushed a flow of 5 till now. So till now, maybe I can put this here also, that the flow which we have pushed from S to T is 5 till now, because I pushed the flow of 5 from here S to T along this path, and that's why we have this sort of capacity. Now we check again. So I'm just doing it. So what in Ford Fulkerson, we just have to find any path from S to T. So we can do it via DFS, BFS, anything. And in Edmund Carp, we do it via BFS. But what I'm doing is just the naive Ford Fulkerson, just finding any possible path and sending flow across it. So this is to demonstrate the concept that actually for the algorithm to be correct and to terminate, we can send the flow along any path. So along all paths is correct. It's just to do the algorithm efficiently. We do it using Edmund Carbs or something like that. But otherwise, choosing any path is fine. So I'll be choosing again some path arbitrarily. So let's suppose now I choose this path to push the flow. The path from S to A, then A to D, then D to T. So there is still a path from S to T. And in this path, there is an edge of capacity 12, an edge of capacity 7, an edge of capacity 9. So the minimum capacity edge is this edge of capacity 7. So I can push a flow of a value 7 along this path from S to A to D to T. So I'll be doing that here. So maybe I can copy this and again, okay, yeah, I guess it makes sense. Yeah. So now this was the path, and now here what we are doing is we'll update the flow to be of capacity. We have now sent a flow of 7 more, so the flow will be 12, and this 7 will become a 0, this 9 will become a 2, and this 12 will become a 5. As we already discussed in the first question, residual capacity is just the capacity minus flow through that edge, and we are sending a flow of 7 through these edges. So again, as we do, we'll add backward edges here, and these backward edges will have capacities of 7. All of these edges will have capacities of 7. So yeah. So yeah. So all these edges now have backward capacity of 7. And now we again try. So and the flow which has been pushed is till now is equal to 12. So now we again try to find out an ST path and whether it is possible to find another ST path. So we can see actually that there exists another ST path. So again, there are many ST paths available to us. But let's say I consider this path, which is from S to C, then C to B, then B to E, then E to T. Note that you can take any ST path and your answer will in the end come out to be correct. But for now, like as we can choose any path, I'm taking this path. The path from S to C, then C to B, then B to E, then E to T. So what's the minimum capacity edge along this path? It's this edge of capacity 4, because S to C is capacity 6, this is 5, this is 4, and this is 7. So I can push a flow of value 4 along this path. Maybe we can copy this diagram and see this ourselves. So suppose I send this. So suppose I have sent this flow of capacity 4 here. So what happens is in this direction, I'm sending further capacity 4 flow. So this 6 will now further reduce to a 2. This 5 becomes a 1. This 4 becomes a 0. This 7 becomes a 3. And in the opposite direction, we can see that this was 5. So we had sent a further flow of amount 4 here. So this 5 instead becomes a 9, because 5 plus 4 will now uh, become actually equal to 9. So I hope everyone is able to understand. And similarly, we'll be adding an edge from E to B with capacity 4 and B to C with capacity 4. So we have reduced the forward capacities and we'll add the backward capacity residual edges. So the graph will look something like this. So this edge becomes an edge of capacity 4, and this edge becomes an edge capacity 4. So I hope everyone is able to follow. So we updated this capacity by increasing it by 4, this backward capacity by 4, this by 4, and this by 4. So something like this. Okay, so we have not updated this capacity yet. So this was earlier a 5, so this will become a 9 because we are using this. So yeah, so 514047539. So yeah, something like this. So this is the updated graph after sending a flow of value 4 along this path. And now we again check whether there exists an SG path in this graph. And we can see that actually there exists another SG path in this graph, which is from this suppose S to A, then A to B, then B to D, and then D to T. And note that the ST path which we are making should not contain any edges of capacity 0. So it's better maybe for us to uh, okay, maybe it's not, maybe we should just say it is. So we need to find out a path which has non-zero capacity also, right? We just don't need a, it's not just that we don't need a path. So this is also a path, the S to C to B to E to T still, but this path has the minimum edges of capacity 0. So along this path, we cannot send a flow. So we have to find a path which contains edges of non-zero capacity. Edges of capacity 0 are not useful for us. So let's just keep this in mind. I don't think it's like this has also been discussed in the lecture, so it's not something very new. So non-zero capacity path will be a path from, let's say, S to A, then A to B, then maybe we can go from B to D and then D to T. So this is a path of non-zero capacity, right? Because from S to A and from A we can't go back, we can't go to D because there's a zero capacity edge. Maybe we can go to B, and from B we can go either directly to T. Okay, this is also a good path. So we can also take this path, in fact. We can go from S to A, then A to B, and then directly from B to T. And along this path, the minimum capacity edges are these edges of capacity 5. So maybe uh, we can send a flow of 5 along these edges. So maybe we can just copy and send a flow of 5, copy this diagram, and send a flow of value 5. So after sending a flow of further of value 5, the flow will become something like 21. And so we'll have to update. So S to A to B to T. So we'll be updating capacities here. So we are sending a flow capacity, flow of value 5 from here, from S to A. So the forward edge will further reduce by 5. So this 5 becomes actually a 0. And the backward edge will increase by 5. So this 7 actually becomes a 12. And now for this edge, this forward edge will have a flow of 5. So this 5 actually becomes a 0. And we'll have to add a backward edge. And this backward edge will have to add a capacity 5. Yeah. So something like this is going to happen. Maybe we can. Yeah. And similarly, this 6 edge, there's a forward direction flow from B to T of capacity 5. So this 6 in forward direction will become now 1. The residual capacity will be 1. And in backward direction, we'll have an edge of capacity 5. Yeah. So something like this. Okay. So now we have to, now the flow becomes 21 and we have updated this graph. Now in the updated graph, we have to find whether there exists another non-zero path from S to T. So we know that from S to A, we cannot go because S to A edge has a capacity of 0. Then the only possible choice is maybe to go from S to C. This has a capacity of 2, so we can go from here to here. Then from C, we can't go to E because C to E again has capacity of 0. Then the only choice left for us is maybe to go from C to B using this edge of capacity 1. And after we arrive at B, uh, we have we can go from directly B to T, but we also have a choice of maybe going from let's say B to D and then D to T. But maybe let's take the shorter path first, like just for convenience. Let's take this path S to C, then C to B, and then B to T. So along this path, there's an edge of capacity 1, there's an edge of capacity 1, there's an edge of capacity 2. So the minimum capacity edge is of capacity 1. So So what we'll be doing is we'll be sending a flow along this direction from S to C to B, and then B to T. And this edge will be a capacity 1. Note that you could also send the flow from S to C to B to D to T of capacity 1. But let's just take this one, just for convenience and nothing else. So let's consider this path S to C, then C to B, then B to T, and then send a flow of value 1. So we can send a flow of value 1 here. Maybe we can update the flow. So let's just copy this diagram. So we are sending a flow of 1. So this flow becomes from 21, it becomes something like a 22. And we are sending this 1 from this to this side. So this 2 becomes this residual capacity of 2 becomes a capacity of 1 because we are sending flow in this direction. This 9 becomes a 10. Similarly, we are sending flow in this direction. So this 1 becomes a 0 and this 4 becomes a 5. And now we are sending again from B to D of 1. So this 1 becomes a 0 and this 5 will become something like a 6. So I hope this makes sense to everyone. So this will be the updated residual graph after sending a flow of 1 along this path. And now actually what we can see is from the source S, uh, if we go to A, so we can't go to A because there's a zero capacity edge here. And from S to C also, uh, we so S to C we can go, but from C you can see that we can't go to E because there's a zero capacity edge here. So and also we can't go from C to B because there's also zero capacity edge here. So actually we can't go from yeah yeah. So actually, we can't go from S to anywhere because if we go from S, the only out neighbors from S are to A and C, but we can't go to C because we can't go to A because there's a zero capacity edge. And even if we go to C, we can't move further because B and E are the only out neighbors of C and both have a capacity of zero right now. So this is the final graph which we obtain, and this will actually be the max flow. So the maximum amount of flow which we can send is something like a flow of 22. So I hope everyone is able to understand. So when I post this document, so when I upload this document, I'll also upload these diagrams. But for now, maybe we can just say that in the answer that the max flow is 22. And we can sort of write down the paths along which we are sending. So answer is the max flow. So max flow is nothing but short for maximum flow from S to T is equals to 22. And how do we do this? So using fourth full person, uh, I'm just writing down the description of the different paths which we took. So this was the initial graph and initially flow was 0. So maybe I should put this also. So yeah, something like flow is 0. And now we added a flow of 5 via the path from S to C to E to T. So initially, so we can take any path, but we are taking this path, let's say, send a flow of initially consider the path S to C to E to T. And what do we see in this path? So I should write clearly. So, so yeah, so what happens in this path is hmm, send flow of 5. And why do we send a flow of 5? Because along this path, the minimum capacity edges of value 5 only. So we can send only a flow of 5. And as soon as we send a flow of 5, we add the opposite edges. Then we consider the path. Now I'll just add the path which we take from S to T. In the second step, the path which we took was, so from 5 we went on to 12. So we took a path of capacity 7, which has been called 7. And the path which we took was something like this, S to A. So we took the path from S to A to D to T. And here the minimum capacity edge was 7. So that's why we can only send a flow of capacity 7 along this path, S2A to D to T. So path is S2A to D to T. And the flow which we can send is send a flow of 7. We can't send a flow of more than 7. You could have sent a flow of less than 7 also and still arrived at the same answer, because in future iterations you could have sent further flows. But let's just say we are just saturating at this point that we are sending the maximum possible flow along this path, which is a flow of 7. So even if you had sent a flow of 6 and added the edges appropriately, you would have in the end arrived at the correct answer, like when the algorithm ends. But let's say what we are doing is right now we are taking the best possible paths. Like we are pushing the maximum capacity at any point of time. So after this, after pushing this flow of 7, sending this flow of 7 along this SADT path, we obtained a max flow of 12. So, and in this graph, now we sent a flow further of capacity 4, which was along this path, something like SCBET. And you can see like, yeah, this was the path S to C to B to E to T. And we sent a flow capacity 4 because here the minimum capacity edge is this edge BE of capacity 4. So the path which we took was S to C to B to E to T. And the flow was send a flow of 4. So this was the flow which we sent along this path. And this was the minimum capacity edge in this residual graph. So note that at all times we are viewing the residual capacities, not the capacities of the original graph, but at all points we are just viewing the residual graph capacities. So after sending the flow of say 4 here, the residual capacity in this direction becomes 0 and so on. And after this, we sent a flow of value equal to 5, which was along this path, S to A to B to D. Right? Yeah. So we sent along this path, S to A to B to T, a flow of value 5. Path which we sent was S to A to B to T. And here the minimum capacity edge was 5. So we sent a flow of 5. And after sending the flow of 5, we update this graph. And in this graph, actually, we could further send a flow of value 1, which was from S to C to B to T. So we send this along this direction. So S to C to B to T. The path which we took was S to C to B, T, and the flow which we sent was send a flow of 1. So the minimum capacity edge along this path was this capacity edge. Okay, this edge of capacity 1. So the flow which we send here is a flow capacity 1. And then we see that after we obtain this flow, then there is no ST path available in this graph, in this residual graph now. So that's why we can actually stop here and we can't send further flow. So now we observe that no path in residual graph of non-zero capacity. So all paths will have zero capacity because all paths from S to T involve some edge which has zero capacity. These edges are the issue here. So yeah, something like this. So we observe that no ST path in residual graph. So no path from S to T residual graph of non-zero capacity. So hence the value of ST max low. So I'll denote the ST max flow as this. The ST max flow is nothing but first we sent a flow of 5, then 7, then 4, then 5, then 1. So this will be something like the final total flow which we sent was 5 plus 7 plus 4 plus 5 plus 1, which is nothing but 12, 16, 21, 22. So The correct answer is 22. Just underlining this for everyone. So yeah. So I'll also attach these diagrams while uploading the document. But right now, let's just. So I hope everyone understands what what we're trying to do here. See. So so this was the second question then. So maybe now we can. I hope it's clear to everyone. Now we can move on to the third question. So the third question says that given a flow network GSTC and a flow F, how will you determine if F is the maximum flow? So suppose we are given a flow network in the graph G, there's a source S, there's a sink T, and capacity of edges is given by the function C. Then we need to find out, and we are also given a flow F, a flow value, flow function F. So this is a function which essentially means that every edge has a flow associated with it now. And now we need to determine if F is actually indeed the maximum flow. So as we already So we need to find out if S is the maximum flow. And I hope everyone remembers from the lectures and this is a property which we use in the second question also, that F is a maximum flow if and only if the residual graph corresponding to F. So corresponding to F, we can make a residual graph, right? Why? How do we do this? We make a graph. Uh, we consider the original graph and then put a capacity and replace capacities of every edge by their residual capacities. And residual capacities were the one which we described in the first problem itself. That when we pass a flow of value 5 through an edge, the residual capacity of the forward edge becomes equal to C minus F, and backward edge becomes equal to F. So that's what we do here. We make the residual graph with respect to F, and then see if there exists a non-zero capacity path in the residual graph. So this is something which was discussed in the lectures also. Okay, so someone has joined the meeting. So hello, Jay. So till now, I have discussed two questions. So this week we are discussing problems related to max flows and four-foot Gaussian algorithm and stuff. So, so first problem was just related to some residual capacities, and then in second problem, I was just demonstrating that how do we find the ST max flow using a four-foot Gaussian algorithm. So we have discussed these two questions, and now we are on to our third question now. So if you have any doubts from now on, maybe you can ask in chat, or if my voice isn't clear or anything, you can also let me know via chat or anything. So yeah. So we are discussing this third question now. The third question says that given a flow network GSTC and a flow F, how will you determine if F is the maximum flow? So as I told you already, as I described already that uh, we say that F is maximum flow if and only if the residual graph with respect to F has no ST path. If there is no ST path, if there is no non-zero capacity ST path in the residual graph in the residual graph with respect to the flow F, then we'll say that F is maximum flow. So the options are if there is any edge that is not saturated to full capacity, then we can conclude that F is not a maximum flow. So this option is incorrect. So there can be edges which are not saturated to full capacity. So for example, let's just consider this graph only. So suppose this graph, yeah. So this is S. This is C. Yeah. So let's just take this vertex as U, this vertex as V. And now we add edges from here to here. This edge has, let's say, capacity 1. And let's say we add another edge. This edge has capacity 2. And we add this edge, which has capacity 1. So we can see here actually that the maximum flow will be a flow of value 1, which can be sent from S to T. So maybe we can see this. And when the flow is of, so in this graph, when we send a flow of value 1 from S to T, So this edge becomes the edge of capacity 0. This edge becomes capacity of 0. But this edge is not fully saturated. Like this edge has a capacity of 2, but only a flow of value 1 is passing through this edge. So note that even though the flow of value 1 was the maximum flow, still we can obtain some unsaturated edges. Like this edge UV will be unsaturated here. So this option A is definitely incorrect. That there can, so in a maximum flow there can be edges which are not saturated. So maybe I should write this in options also. So answer is option A is incorrect. And why is this incorrect? In the given figure, so I'll add this figure later, but for now I'll just describe edge UV is not saturated in the maximum flow. So in this given figure, edge UV is not saturated in the maximum flow, which is of value 1. So yeah, option A is incorrect. The option B says if the residual graph does not have any augmenting paths, then F is a maximum flow. So yeah, actually option B is the correct answer. So the ST paths in the residual graph are also known as augmenting paths, as was discussed in the lectures also. So yeah. So if we can't find any augmenting paths, which are basically the non-zero capacity ST paths, then F is actually a maximum flow. So option B is correct. So, so this is by definition itself. And similarly, it can be seen that option C says if the value of the flow F is not sum of capacities of edges coming out of the source S, then F is not a maximum flow. So this option is incorrect. Like there can be flows where so the option C says that a flow F is not a maximum flow if the value of the flow F is not the sum of capacities of edges coming out of the source S. So this option is also incorrect. Actually, there can be maximum flows where the sum of capacities of edges coming out is not equal to maximum flow. So consider the examples, similar example, but we change the capacities. So suppose here I put a capacity of 2 and here I put instead a capacity of 1. So here you can actually see that the maximum ST flow in this example is again a flow of value 1 only going from S to T. So, but the sum of capacities going out from, okay, maybe this is a good example. So yeah, so sum of capacities going out from S uh, is equal to 2 actually, but the maximum flow is equal to 1 still. So even though the flow of value 1 is the maximum flow, uh, but the sum of capacities going outside is 2. So we can't say that maximum flow is always equal to sum of capacities going outside from S. So this option C is incorrect. So option C is incorrect. As in the given figure, the figure is the one which I just described. Sum of capacities uh, coming out of source S, sum of capacities of edges coming out of source S is equals to 2, but max flow is equals to 1. So yeah. And similarly, option D says if the value of F is not the sum of capacities of edges coming into the sink T. So here there was coming out and there is this option of coming into the sink T. So in the same diagram, you can see that the sum of capacities into the coming into the sink is also equal to 2, but still the max flow is still 1 in this graph. So the same example for is a counter example for both option C and option D. So yeah. So option D is also actually incorrect. Incorrect. And the reasoning is reason is similar to option C. So yeah. So hence Option B is the correct answer. So only option B is correct. Hence, option B is the correct answer. So note that there could have been multiple correct answers, but in this specific question, there is only one correct answer, which is option B. So yeah, I'll just underline this for ease. Okay. So now we are coming on. I hope this is clear. If this is not clear. Okay, so Jay, I just saw your question, so sorry for this. So Jay is asking in the chat, what is a residual graph? So I was explaining the residual graph initially also, right? So did you catch that, Jay? So I was explaining that what's the residual capacity of an edge. So if we pass a flow of value f through an edge of capacity c, the residual capacity of the forward edge becomes equal to c minus f, and residual capacity of the backward edge becomes equal to f actually. So the residual graph is just the graph, uh, the original graph, but having residual capacities. Something like that. So if every edge has the capacity, if we instead of writing down the capacities of edges, we write the residual capacities of edges, then we call the graph as a residual graph instead of the original graph. So we had also done the example here. So this was suppose this was the initial graph given to us. And now let's suppose I send a flow of value 5 in this graph along this edge. Let's say I send a flow along S to C, then C to E, then E to T path. And I send a flow of value 5 because 5 is the minimum capacity edge along this path. So I send a flow of value 5 along S to C, then C to E, then E to 12. So what happens is in the forward direction, I'll reduce the capacities by 5 for these edges. And in the backward direction, I'll increase the capacities by 5. So what happens is all the other edges remain same, but along this path, the original capacity was 11. So now I reduce it by 5. So this 11 becomes a 6. And I add a backward edge of capacity 5. Similarly, from C to E, the earlier capacity was 5, so it becomes a 0. And now in the backward direction from E to C, we add an edge of capacity 5. And now similarly from E to T, there was an edge of capacity 12. So this 12 becomes a 7. And then from T to E, we add a backward edge of capacity 5. So now this graph is the residual graph with respect to this flow, the flow which we sent from S to C to E to T. So so this is the high level intuition. So is this idea of residual graph clear to you, Jay? Okay, so you got it. Nice. So if you still have any doubts, then you can also view the lecture videos because this has been discussed in this week's lecture videos also. But this is more or less the high level idea that adding these backward edges of equal capacity and forward edges and reducing the capacities on forward edges. This is what we call a residual graph. And yeah. So, and in if the residual graph does not have any augmenting paths are just ST paths, which have non-zero capacities, then that is called, uh, and that's when we call that the given flow is a Mach flow, something like that. Okay, so then maybe we can move on to the fourth question. So fourth question says that an electrical circuit is modeled as a network from source to ground. Three lines from the source with a combined transmitting capacity of 5 units per hour. Two lines end in ground with a combined transmitting capacity of 4 units per hour. And the in-between networks are unknown. So the problem says that an electrical circuit is modeled as a network from source to ground. So basically what this means is that the electricity is being sent. So source is the electricity source and ground is somewhat of an electricity sink. So from source, there are three lines going out with a combined capacity of 5 units per hour. And two lines are ending in ground with a combined transmitting capacity of 4 units per hour. And what we are also given is that the in-between networks are unknown. So we don't know which line is going where, which other line is going where, and so on. And now we want to find out the maximum transmission capacity of the electrical circuit. So note that I believe this might not have been covered in the lectures, I don't remember, but an electrical circuit can be modeled as a max flow only, right? Because suppose this this was the source and this was the sink, and suppose these are the wires of given capacity. So one wire has a capacity of one has a capacity of two, this has a capacity of one. Then we are supposed to, and suppose in this graph we want to find out what's the transmission capacity of the network. Then it can be seen that the transmission capacity of this network will be equal to one only, even though this wire has a capacity of two. But due to these wires, due to constraints on these wires, which are capacity of one, we can only send a current of 1 ampere through source to sink here, right? Similarly, in this example also, we can send only 1 ampere from source to sink. And note that so the electrical circuits can be modeled. So electricity can also be modeled as flows, because a current is nothing but somewhat of a flow going from source to sink only, right? So I hope you get the intuition for this, like why is current actually similar to flows. So what this means is that electrical circuit can be modeled as a network from source to ground, where ground is the sink. And we are given that three lines from the source with a combined capacity of 5 units per hour originate. So what we are given is, so from the source, so there is some, so what we are given is, maybe I should draw a diagram. Uh, so we are given the source and we are given the sink also. And we don't know the network in between. So there is some network in between. Some network. And we are given that the lines transmitting out of source. So there are three lines which are transmitting out of source. So there are three lines which are transmitting out of source. So let's say these are three lines. And similarly, there are, this is ground, or we can say the same T. And we are also given that there are two lines which are going inside the ground from this network. And we are also given that the sum of these three edges, the sum of transmission capacities of these three edges is nothing but 5 ampere or 5 units per hour, because it's given that three lines from the source with a combined transmitting capacity of 5 units per hour. So sum of these three is equals to 5. So these are capacities, let's say C1, C2, and C3. The sum of these capacities is 5. Maybe I can denote it by this. So sum of these capacities is nothing but a 5 units per hour. And similarly, we are also given that two lines end in ground with a transmitting capacity of 4 units per hour. So two lines end here, and they have capacities of 4 units per hour. So the combined capacity or the combined sum is 4 units per hour for these two, right? So I hope you get the question. And now the problem says that, and the in-between networks are unknown. So we don't know about this network, what lies inside, what's the transmission capacity here. And now the problem asks us, what is the maximum transmission capacity of the electrical network? So, the maximum transmission capacity is nothing but the maximum flow, which we want to find out of the given network. Because as I already said that like these capacities can be modeled as max flows also. So what is the so basically we need to find out the maximum flow in this sort of graph. So if we are given some sort of a graph where this source is the source S and this ground is the sink T, and we know that some of these pages is 5, these is 4, and the network inside we don't know. It can be anything. So inside the network there may be 0 capacity edges, there can be 1 capacity edges, there can be 100 capacity edges also. So now the problem asks us what is the maximum transmission capacity? And the options are 4, 5, 9, and not enough information. So Jay, would you like to try out this question? Like, would you like to, what do you think would be the answer? Would you like to answer? Like, which of these options should be correct according to you? Okay. So Jay is saying no idea. So actually, in this problem, actually, since we don't know what lies inside this network, the answer will actually be not enough information because the maximum flow can be equal to 4, but it can also be less than 4 also. Suppose inside this network, there were just 0 capacity edges. Suppose inside this network there were just 0 capacity edges. And since there will be if there are only 0 capacity edges, then we can't send any flow from source to sink, right? So in that case, the flow will come out to be actually 0. Whereas suppose inside the network there were a lot of 100 capacity edges. Suppose from this edge to this edge there was a 100 capacity edge. There from this edge to this edge there was a 100 capacity edge. Then we could actually send a flow equal to 4 from source to sink. So the answer will actually change according to the edges present inside the network. So if the edges inside are such that so edges inside can be such that we can send a flow capacity 4. It can also be such that we can send a flow capacity 0. So that's why the answer would be actually not enough information. So to solve this problem, actually, we need to know what lies inside the network also. So the correct answer is option D, actually. So option D, the correct answer. As information about the network inside is also needed to find out the maximum flow in the network. So, so yeah, something like this. So again, while uploading, I'll post this diagram along with this. But yeah, I hope you get the idea. So I'll just underline this also. Okay, so now we have this fifth question. Okay, I, yeah. So the fifth question says that a man has two kids who keep fighting. So a man has two kids who keep fighting. When on their way to school, they want to make routes such that they both don't have to travel through the same road. So what we are given is we are given two kids who keep fighting, and on their way to school, they want to take routes such that they both don't have to travel through the same road. And we are given the map from their home to the school S, which resembles a directed acyclic graph. So we are sort of given a directed acyclic graph, and we want to go from home H to school S in the graph. And in the graph, what we want is can we implement some algorithmic technique to determine if both kids can go to the same school without having to travel through the same roads. So what we want is that the two kids to travel entirely different roads, to travel two entirely different paths. So is it possible for us to determine using algorithms if we can go? So So any idea, Jay? Would you like to think about like the options are A, B, and C? So this is actually somewhat this problem would be this a very similar problem is present in your this week's quiz or this week's assignment also. So I believe this is an important problem for you guys. So actually, the key idea here is uh, nothing but that we have two kids, and for these two kids, what we want is we want to send them from one vertex, let's say home H, to another vertex, which is let's say the school S. So we want to send these kids from the vertex H to vertex S along two different paths, two totally different paths. So if we want to send them along two totally different paths, so what we actually want is to determine and so what we want is no both kids should travel different roads. Like on one road, maximum only one kid can travel. Both kids can't travel through the same road. So if we sort of uh, attach a capacity to every road, so what we want to do is we want to have each road to have a capacity of one. That each road can take only one kid with it. And if we do something like this, then we just need to find out the max flow from H to S. So if we find out the maximum flow from H to S, this max flow will have to be greater than equal to 2. If we are able to find a max flow value greater than equal to 2 from H to S, if every road's capacity is 1, then actually what this means is that the two students can take entirely different paths, because if max flow is greater than equal to 2, let's say max flow is equal to 3, then what this means is that we can send flow along three different directions. So we can select any two of these directions. And in these two directions, the uh, roads will sort of not intersect. And so, yeah, so we'll be actually able to obtain two different paths. So something like this. So the answer will be something like this. So run forward full custom algorithm on the given graph with edge capacities as one. So we take the edge capacities. Uh, so we take something like an edge capacity as one. And if max flow comes out to be greater than equal to 2, then both kids can go to the same school without having to travel through the same roads. So this is a concept which you can study by yourself also. So this is called something like an edge disjoint paths. So this is something like finding out the number of edge disjoint paths. And that problem essentially reduces to finding out the max flow only. So yeah, so the problem can be actually solved by this, that we keep all the edge capacities as one, and then we find out max flow from H to S. So the max flow will be calculated from H to S. From H to S comes out to be greater than equal to 2. Then both kids go to the same school without having to travel through the same road. So yeah. So the other options are if count is greater than equal to 2, where count is the number of times S is encountered in a single run of some modified DFS. So this is incorrect. Similarly, if the max flow through the graph is greater than equal to 1, then both kids can go to the same school without having to travel through the same roads. So this is clearly incorrect, right? Because from H to S, suppose there is only one road of capacity 1. Then what this means is that both kids will have to take the same route, but the max flow will be greater than equal to 1. So this option is sort of incorrect. So option C is the only correct answer. So I believe to get an intuition of why is this actually correct, you guys have to read some stuff yourself, which is very cool stuff. So I'll encourage you guys to read about it also, because math flows are very essential part of algorithm. So you guys should know stuff about math flows. So option C is the correct answer. Uh, num so the maximum the number of edge disjoint paths. So edge disjoint paths means that two paths in which no edge is common. So here edges correspond to roads. So we need to find out the number of roads, the number of paths in which no roads are common, something like that. So the maximum number of edge disjoint paths in a graph, S to T in a graph, can be found using ST max flows. And this is something you guys should read because this is very cool stuff. So, yeah. So yeah, something like this. Or maybe this will be something which comes up in next week's lectures also. But yeah, you guys can see this yourself also. So option C is actually correct. So whenever we want to find out the number of edge disjoint paths, suppose we want to find out if there are k possible edge disjoint paths between source to sink. So what we do is we just assign every edge a capacity of 1 and check whether from source to sink the max flow is greater than equal to k. If it is greater than equal to k, then there are k edge disjoint paths available. Here the edges correspond to roads. So yeah, so here the problem becomes in terms of roads, but in terms of edges or roads, it's the same. So something like this. So here option C is correct. Then after this, maybe we can move on to the next questions. If so, yeah. So for question 6 to 8, so these questions are also present in the in this week's ungraded assignment. So, or maybe next week's ungraded assignment. I don't remember, but yeah. But these are some questions which we can do by ourselves right now also. So we are given two arrays M and W, where Mij gives the number of matches left to be played between teams I and J. Wi gives the number of wins till now by the team I. So we are given two arrays. One is M, which corresponds to matches, and W array, which corresponds to wins. So M is the 2D array, W is a 1D array. So and Mij gives the number of matches to be played between I and J. Wi gives the number of wins till now by the team I. So suppose I want to know how many wins. So suppose we are organizing a tournament. In that tournament, uh, some matches are left between some teams, and some teams have already won some matches. So this M and W gives us all of that information. So let's say the index of our team, we are also playing an index of our team is N. And now we decide to reduce the problem to max flow by constructing a graph G in the following manner. And how do we construct the graph G? So for every unordered pair of teams Ij, create a node Mij, and for every team, create a node Ti. And add edges from source S to all Mij with weight Mij, and add edges from Mij to Ti and Tj of capacity X1, and add edges from all Ti to the sink with weight X2. And then we need to answer the following questions. Okay, so maybe I should. So this sort of problem and this sort of diagram has already been discussed in the lectures in the lecture of like eliminating sports via something like sport flow or something was the lecture's name. I don't remember, but in this week's lecture, this sort of setting has already been discussed. But still, I'll discuss it so that you guys get a better understanding out of this. So what we are given is a so we were given these two arrays M and W, and Mij gave the number of matches left to be played between I and J, and Wi gave the number of wins till now by team I. And now we construct a graph G in the following manner. So for every unordered pair of teams Ij, so I create a node Mij. So let's say I create some nodes here. So let's say this is the node which I construct. This node, let's say I call this M11. And similarly, let's say I construct further nodes M12 and something like this. So M11, M12. So maybe M11 is not relevant because one does not fight with itself. But maybe let's say something like a M12, M13, and we go on till like Mij. So something like, let's say we have some nodes Mij here. Yeah. So this is the graph G. In the graph G, we have some nodes on this side, M12, M13 till Mij. And for every team, we create a node. We create a node Ti. So these are the matches which are left to be played. We create nodes with respect to the matches which we want to play, and we also create some nodes with respect to the teams that are playing. So something like so team one, team two, till let's say some team Ti. So there are some teams which are playing, and yeah. So we have created some nodes with respect. So I'm just drawing the graph which they intend to draw. I'm just giving a pictorial representation for this graph G. So we create nodes Mij, and for every team we create these nodes Tis. And now, okay, and now what we need to do is we add edges from source to all Mij with weight Mij. So we create a source also. We create a source vertex also. Let's say we call this source S. And I create a sink vertex also. So they create a source as well as a sink T. Right? So let's say I call the sink T, the source as S, this T1 to Ti. Note that this T is the sink and these Ti's are the teams. So these T's are different. And now I add edges from source to all Mij with the weight capital Mij. So here, so I add an edge from here to here, and this has a weight of M12. Similarly, this edge has a weight of, so this edge has a weight of M13. And similarly, this edge has a weight of Mij. So something like this. So these are actually some values which will be given to us via the M matrix. And similarly, we add edges from Mij to Ti and Tj of capacity x1. So what we do is we add edges from Mij to Ti and Tj of capacity x1. So suppose, so there is this team Ti and there is some team Tj also here. So let's call this team TJ here. So there is, and now what we are doing is we add edges from Mij to Ti and Tj of capacity x1. So from this Mij, we add edge to Tj, and this edge has capacity of x1. Similarly, we also add Mij to Ti, and this edge also has capacity x1. So I'm not doing anything. I'm just drawing out the diagram of graph G as is given in the problem. So this is something which you will also need to do to get a better understanding. And also we add edges from all Ti to the sink with weight x2. So from all Ti, we add edges to the sink with weight x2. And we don't know what this x2 is, but maybe I just put down this as x2. So something like this. And this is what we do for all the teams. But yeah. So this is the graph which we have sort of constructed. So we'll be constructing these sorts of edges for M12 also, like we'll be drawing edges from M12 to T1, M12 to T2 also. Similarly, we'll be drawing edges from M13 to T1, M13 to T3. And similarly, I'll be drawing edge from Ti to T, T1 to T, T2 to T, and Tj to T also. But I'm not drawing all those edges because it can cause a bit of a confusion or it can cause a ruckus. So for now, let's just see these edges, which are first x1 and x2. And now, uh, we what we want to find out is we decide to so we want to uh, answer the problem which was uh, answer the problem which was discussed in the lectures also. So what we want is, suppose we are the team N, and what we want is whether to check in the that suppose we are given these matches, the remaining matches which are left to be played, and we are also given the wins which every team has accumulated till now. And now suppose we want to check whether we can win the trophy or we cannot win the trophy. So this was an example given in the lectures also. So are we can we win the tournament or can our team not win the tournament? So this is something which we want to check using max flows. So for this, it was just in the lecture that we can draw a graph like this, and we we would be able to check whether we are able to win or whether we are not able to win the trophy. So for this, uh, what we actually do is we assume that, just to recapitulate what was discussed in the lecture. So what we assume is, suppose our team wins all the remaining. So suppose our team is nth team and suppose it wins all. So suppose we want our team to win the trophy. So the best case scenario would be when our team wins all of the remaining matches, right? So if our team wins all of its remaining matches, that would be the best case scenario for us. So if our team wins all of the remaining matches, then what we want to find out is, if our team wins all the remaining matches, is there any other team which can win more matches than us, even in the best case? Like in so can is does there exist, or does there always exist a team which will win a trophy over us even if we win all our matches? So that is something which we want to find out. I hope problem is clear, that we want to, even if I win all of my remaining matches, will there still exist a team which can win the trophy instead of me? So this is something which we want to find out. So yeah, so something like this is the case, that even if all the other results go my way, like suppose my opponent teams always win or lose such that it is in best interest of mine, but will I still be able to win the trophy or will I still not be able to win the trophy? So something like that. So for details, you can refer to the lectures also. This problem has been discussed in the lectures as well. And now we want to find we want to answer those questions using this graph G. And so for answering this question, the sixth question asks us, which of the following can be the value of x1? So x1 was the edges added between mij to ti and mij to tj. So the problem asks us, which of the following can be the value of x1? So what are the edges? What do these edges x1 actually denote here? Uh, so actually these edges x1, what do they actually denote is whether uh, this match, let's say this the teams which have mij, how many points will they so this x1 actually denotes how many points can mij contribute to tj and how many points can mij contribute to ti. So let's say teams ti and tj play 10 matches. So suppose this mij is 10, then what happens is, maybe all of the 10 times this tj can win, or maybe all of the 10 times ti can win, or maybe they can share five points in between themselves. So this is something which we'll want to find out using max flows, that how many matches should each of these team win so that in the end our nth team wins the trophy. But in the worst case, so we want in the worst case, these the value of x1 can go to as large as mij's, because all of these matches can be won by the team TJ, or all of these matches can be won by the team TI. Uh, I hope this makes a bit of sense to everyone. So actually, this x1 will have to be take the value of mij, because x1 denotes the maximum number of matches which a team can win. And since there are mij number of matches, so x1 will be nothing but equal to mij. So that's why here the correct answer would be option A, mij. Option A is the correct answer. And the intuition is that a team TI can win all of the remaining mij matches against team TJ. So something like this. And that's why the maximum value of x1 can be mij. So that's why we need to put the capacity as mij between edges I and j. So for understanding this a bit better, maybe you can first go to lecture videos and see the lecture corresponding to this paragraph. And after that lecture, maybe you can come back to this problem, and I guess then it will start making a bit more sense. Now, the seventh problem says that, so what should be the value of x2? So what should be the value of x2 here? So x2 is, so suppose even if our teams, even if our team wins all of the matches, okay, so even if our team wins, yeah, so we want to find out the max flow, and yeah, so what we want to find out is uh, even if our team, the nth team wins all of its matches, even then maybe it is possible that so let's consider this team TI. So suppose this team TI has right now WI wins, and my team has currently WN wins. Now, even if I win all of my remaining matches, now I am the nth person, and suppose I win all of my remaining matches, then what actually happens is uh, it may be possible that uh, TI can still overtake me. So suppose I win K number of matches. So suppose in the okay. So suppose I win all of my remaining matches. I'm the nth team, and even if I win all of my remaining matches, even after that, what can happen is this TI maybe can have WI wins, and these WI wins. So suppose right now TI has WI wins, and I have something like WN wins. But now, as I play, I'm the nth team, and I play even more matches. Maybe I can win all of my matches. But it may be possible that the value of WI will also increase because TI can also play some matches. So it may be possible that WI overtakes the value of WI in by the end of the tournament or something. So we want to find out, is it always possible or not? And this was discussed in the lectures that actually for this edge x2, we can put the capacity as uh, the maximum number of matches which TI can win without overtaking our team N. So X2 is nothing but the maximum number of matches which the team TI can win without overtaking our team N. So that should be somewhat of the answer. So what should be the value of X2? So X2 should be nothing but the X2 is nothing but the number of matches which the team TI can win without overtaking our team N. So maybe I should write down this intuition here. X2 should be equal to the number of matches uh, TI can win without overtaking team TN if TN, so even if TN wins all of its remaining matches. So if TN wins all of its remaining matches, even after that, we want to constrain that TI should not overtake TN. So this is something which we want, and for this, what we can actually see is the number of wins TN has after winning all of its number of wins TN has right now. So right now TN has WN wins, right? Because that was how we defined the WN array. So WN array was defined as the number of team wins till now by team I. So WN gives the number of wins by team N. And number of matches left. So we want to find out how many matches can the team N win? Can the TN team win? If it wins all of its remaining matches. So for that, we want to find out the number of remaining matches of TN. Number of matches left to be played by TN. So number of matches left to be played by TN is nothing but the number of matches which TN needs to play against all of the teams. So it will be something like a summation of Mij, where I is equal to N and J varies from 1 to N, something like this. So this Ri gives nothing but the number of matches which are left to be played for the ith team. So I hope everyone gets the idea. Why is this the case? Because we fix an I and we see how many matches this ith team has to play against team 1, team 2, team 3 till team Tn. So this when summed over all then gives us the total number of matches remaining. So Rn will give us the number of remaining matches. So the number of wins Tn can accumulate, number of wins Tn can have at the end is equals to Wn plus Rn. So these are the number of wins which Tn can have at the end if it wins all of its matches. And what we actually want is hmm, uh, so now what we actually want is and this x2. So what we actually want is this team Ti number of wins Ti has right now is some nothing but W of I as was given to us in the problem. The number of wins Ti has right now is Wi. And now what we actually want is x2 should be equal to number of matches Ti can win without overtaking Tn. So what we actually want is Wi plus x2 should be less than equal to, or maybe let's say in the worst case it will be equal to, because we don't want overtake, but it can actually be equal. So in the worst case, the number of wins which I has right now plus the number of wins I accumulates afterwards will be equal to something like Wn plus Rn, which is the number of wins by the nth team, right? So from this, we actually get x2 equals to Wn plus Rn minus Wi. Wn plus Rn minus. So this might be a bit dicey for someone who is new to this problem. So understanding this might be a bit dicey, but trust me, once you go through the lecture related to this problem, so it's the sports mode lecture, or I don't remember the correct name, then you'll be able to understand what I'm doing here. So this will be the final answer. And this is option B here, Wn plus Rn minus Wi. So yeah, we actually put it in bold. So hence option B is correct. Yeah. So this is the correct answer. And yeah. So now comes the eighth question. Which of the following approaches will work on the graph G created? So this also is just a direct question which was discussed in the lectures. So here what we do is we run a max flow on G and return yes if all the edges out of the source are saturated. So if this is true, then we return a yes, because then this means that there exists an win-loss assignment of matches so that uh, our team can win the tournament. So yeah, so something like this. So option A is correct here. So answer is option A is correct. And you can see the reason that this has already been discussed in the lectures. Yeah. Okay, so I guess these were all the questions which I had for today. So I guess this sums up the question answer session for us for today. So Jay, if you have any doubts or any comments, maybe since we have some time, you can ask me via chat. Or if you don't have, then we can also close the session. So if you have any doubts, maybe I can take those. Otherwise, we can maybe close the session. Okay. So Jay is saying that he has no doubts. So just keep this in mind, guys, that the question 6 to 8 might seem tricky to you, or you might not understand what are we doing here, or why are we drawing this sort of diagram here. But just trust me, like first go through the lecture videos, and after that, I believe a lot of this should start making sense for everyone. So yeah. So other than that, since Jay is saying that he has no doubts, I guess uh, we can stop the discussion for today. So once again, thanks for joining, and thanks to everyone on YouTube who's for watching this session. And yeah, we'll meet again next week, same time, Tuesday, 6 to 8 p.m. So hope to see you guys then. So for now, I'll stop sharing, and yeah, I guess we can say goodbye. So bye bye, guys. So you can also leave the session. Yeah.